Yeah, hello everybody. Statistics, and I uploaded some exercises we will do today together, and I will also announce that I have organized a talk or a panel discussion with some guys. Dr. Jörg Rahn, he is, investment officer, chief investment officer of a family office. This means very rich people asking somebody else how to invest in the financial sector. I think it will be very interesting what such a guy says in these very volatile times. And also Dr. Wolfgang Kornprobst, he is in the economics strategy part, working at Siemens, and one of these global players. What shall we do? Shall we move to the United States in order, or because of the maybe coming tariffs when we want to export to the United States, or do we sell our goods to other countries? What else? I think it will be very interesting to hear these guys. 15th of May, 10:15 until 11:45, and it will be also hybrid, so you can log in via Zoom. And another one is, as students, I want to visit the Yara Visa port on 1 week later, 22nd of May, starting there at the visitor center at 10:30, and please sign in the Moodle course. And if you say yes, then also please come, because I have to charter a bus that we can go on the harbor area. And well, the size of the bus, of course, depends on the people who want to come. And afterwards, chartering a bus for 50 and only 17 of you are only showing up. This is not that nice. So please, until next Wednesday, 12 o'clock. Sign in the Moodle course. Okay, then we want to start, since we have talked about confidence levels, confidence intervals, so to speak. We have started with causality in statistics. Until now, we have only talked about descriptive, calculating an average, calculating volatility via variance or something like this, but we couldn't deduce right now, well, I see this in the data and this causes some behavior of my economic agents or something like this. And now we want to take, we are taking the next step, that we have introduced the so-called confidence intervals, and behind this is the thinking that you say, well, of course, I have not asked everybody in Wilhelmshaven, only 1,000 people. And from this, I want to make a conclusion about the behavior of all consumers in Wilhelmshaven, of all 80,000 people. And since I haven't asked everybody, I have to ask how, so to speak, in quotation marks, good are our estimates. And for this, we then calculate, for example, the average of our 1,000 answers. And then, since we know that we do not hit the true value, because we haven't asked everybody, or there is a probability that we don't just hit the true value of the whole sample. Therefore, we say then, okay, we give us a limit of how quantitatively we want to rely on what we make for a conclusion. And let's say with an error probability of 1% or 5%, we then ask, well, can I rely on my outcome of my statistical experiment, of my survey data, or whatever? And then we introduced that we assuming a special distribution of my data, and in general, think of the central limit theorem. Quite often it is a good assumption to assume that my data is normally distributed. So given the normal distribution, given my data outcome, and given my error probability, then I can calculate an interval which is then 1 minus error probability 1 with minus 99% the true value when it is symmetrically assuming a normal distribution situated around my descriptive arithmetic mean, which I have calculated out of a data. And be careful, this interval or the limits of the interval are also random variables, because quite often it is then said with 99%, the true value lies in between this interval. And this is statistically wrong. This interval covers with 99% the true value. So the limits, they are also, so to speak, volatile. They are not fixed. Okay. And having this, we want now to do some concrete calculations. Let's start with, within a sector, we have N equals 12,100 single firms. I don't know, regional pharmaceutical sector or something like this. And since we have not the total statistic, we have drawn a random sample that we just went to 225 of these firms out of 12,100. And there we collect the data and obtain every single profit. And then, having these 225 single profits, we calculate the average profit of 600,000 and a standard deviation of 90,000 euro. So to speak, descriptively, we say that within this sector, we have earnings of, on average, 600,000 plus minus 90,000. First of all, calculate the standard deviation of the average. Well, the standard deviation, sigma, is given by 90,000. And then we have talked about this, we have introduced this, that the volatility of the average is scaling with the number of our sample. And how is it scaling? It is not directly scaling, so divided by n, but it is scaling with the square root of n. So A then would be that we obtain the estimator of x bar is our descriptive volatility divided by square root of 225, and therefore you see that I have chosen 225 because the root of 225 is just 25. So 90,000 divided by 25 is 60,000. Why do we need this? Well, this average, or not this average, this standard deviation, we just plug in into our plus minus for the confidence interval. So then B, calculate a confidence interval of mu, the expected value, for an error probability of alpha equals 5%. Well, this is then a two-sided confidence interval. So the tails on the left and the right, they have a mass, probability mass of each 25%. And then, since n equals 225, larger than 30, then we can choose the normal distribution. And here I have shown you again the table of the normal distribution. There we could just look up the 95. There we have to choose this 97.5. Again, symmetrical distribution, 2.5 to the right, 2.5 to the left, and 1.96 we have as the limit value of the standard normal distribution. And here we see this to the picture from the lecture. Well, and then we can just insert our limits we have given, average of our sample minus z 1.96, 1.96 plus standard deviation of the average and minus standard deviation of the average. So the upper limit, theta bar, equals then 600,000 plus 60,000 times 1.96 and P lower bar 600,000 minus 60,000 times 1.96 is 558, 240 and 611, 759. Well, and now in order to compare the aggregated sectors, we maybe are also interested in the confidence interval of the whole revenue, the whole profits, the aggregated profits of the whole sector. And now, in order to change something, we say with an error probability of alpha equals 1%. And for this, remember that the expected value is just a linear operator, E of ax plus b was a of e of x plus b, and we had the variance of ax plus b is just a squared variance of x. Well, therefore, the standard deviation of ax plus b translates then, of course, in standard deviation of x. And therefore, we have just to scale our new numbers calculated with an error probability of 1% with the size of our sector 12,100 firms. So in the end, we obtain as the limits of the whole sector with an error probability of 1% would then be equal scaling factor 12,100, and now the same, but here we have to insert the corresponding Z value, which corresponds to 99%. So let's see, where do we have roughly 99, then 99.5. This is almost this one here. So 2.58, and this we have also here. So this is 600,000 plus minus 60,000 times 2.58. And so in general we obtain theta upper bar is 7.07. In English it is billions euro, and P lower bar is the other way around. This is P lower bar and this is P upper bar, 7.44 billion euro. Yeah, and that's it. And then we had some other examples in the lecture, and we will go through these other examples. Because now, let's go to another exercise. A machine is cutting steel rods of a specific length. Out of a total production of N equals 150, we take a random sample of N equals 9, measuring their length. So, and these are all our single values. So, x1, x2, 3, 4, 5, 6, 7, 8, 9. And since this machine has been running for the last 3 years, we roughly know that overall in history this machine has cut, let's say, 20,000 steel rods, and we have put in these data, looking at these data, and we found out, well, approximately we can assume that the whole production is in general normally distributed. So we assume that the overall distribution behind our random sample is normally distributed. What is now the difference compared to the first exercise today? Well, this 9 is different. And there I talked about this guy from the Irish brewery who has thought of experiments where the size of my random sample is very low. And there he found out, well, in generally we can approximate the distribution of our sample with the normal distribution, but the smaller our size, the worse is our approximation. And then he found out, well, it is better to underlie a new distribution, which is now depending on the size number. Remember, when we have normal distribution, whatever, if the size is 100, 1,000 or whatever, the normal distribution looks always the same. Here, this is not the case anymore, because this one we call then the T distribution or the student distribution. Student because he has published his paper under the pseudonym student. So 9 smaller than 30, and then we have to take the T distribution. Well, taking the T distribution, this I have introduced in the last lecture. Then almost everything is the same, but here we have to interchange the Z value of the normal distribution with the T value now, Tn minus 1, depending on the size of the sample. So this was done like this, hopefully. Yes, I'm still right. Let me cut this. And that we see it in our exercise. We put it in here. So, and as I mentioned, the whole tables I put on the internet, and here we have the T distribution number 7, normal distribution, here we are. And here we see, well, it is not that easy to plot this just in a PDF, because now it is not enough to plot only one table. We have in general to plot a table for every number of the sample size. So to speak, let's start in general. We say a large number in statistics is starting at 5, and therefore, because with asking 5 people, you roughly can start to calculate something like an average, and you can deduce something from these average. So then we would have to write down a table for n equals 5, 6, 7, 8, 9, 10 until 30, when we then assuming that the approximation of the normal distribution is okay. Well, this would be then 25 tables, 25 pages. Well, since we in general see that we are not choosing always some really very specific error, probability error values. Therefore, in these tables, we plot only some numbers corresponding to error level of 5, 5%, 1%, 0.1%, or 10%. And this we see here. So this means then 90, 95, 97.5, and so on. So, but here we have to be careful. These are one-sided values. So if we want now to look up the error value, the t value for a 5% symmetric, again, confidence interval, then we have to look not at the 95%, but at the 97.5%, the same as we had with the normal distribution. So, okay, then at first, we want to calculate an unbiased estimator for the mean and the variance of the parent distribution. And there we have to be a little bit careful. The first, the average, this is not very hard. This is just the arithmetic mean. So 1 over 9 times 1 x1, x2 up to x9, and the outcome is 184.8. And now here we have to be a little bit careful. The estimator for the variance is given by 1 over 9 minus 1. I will see if you have time to show where this factor minus 1 is coming from. But then the estimator is not biased. And this was one of the properties which we want to have, that we do not make yeah, an error where we are secure that we always make this error. On average, we want to hit the right value. So then we have this, and sum over n equals 1 to 9 x1 xi minus x bar squared. And this is then 1.725. Well, having this, now calculate a confidence interval for confidence levels of 90% and 99%. 90%, then again, we have to be careful. We have to look at 0.95 symmetric, 5% in two directions. Every tail has probability mass of 5%. And then n minus 1 means 8. So I obtain for the t value first p equals 10%. Then the t value equals 1.86. And p, not, yeah, 10%, p equals 1%. Then we have to go here, 99.5. Same argumentation. On the right, on the left, we have 0.5% probability mass, 3.36. So t roughly 3.36. And then again, we have only just to plug in these numbers. So we would then have theta lower upper bar would be average 184.8 plus minus the first one, p equals 10%, 1.86 times sigma over n, and now it's over n. Square root of 9 is by accident just 3. So we have then 1.725 over square root of 9 is then p lower bar 183.99, p upper bar is 185.61. 185.61. And for p equals 1%, let's do this in another color. The only thing which is changing that we have to insert here 3.36, and we obtain p lower bar is 183.33, 183.33, and p upper bar 186.27. Yeah, of course, all this we can plug in a software package and pressing enter, but you really should keep in mind what is, so to speak, the picture behind this, and this is the same picture which we had when we have looked at the normal distribution. So here t distribution x, and in the first one it meant, well, this probability mass here under the density function of the t distribution is 90%, and then this is 561, and this is 1839. 9, and the other one 10. And there you see, of course, the smaller the probability, error probability, the larger has to be the confidence interval, because now the probability mass measured by the area under the density function has to be now a value of 0.99, and then we had this as the lower limit and this as the upper limit. Okay, next step. There we have talked about quite often, we have these so-called Bernoulli experiments, outcome 0 and 1, lose and win, loss, success. And then we can somehow come to our aim a little bit faster. In general, it is just also the average relying on the normal distribution, because the part, think of flipping a coin 11 times and having succeeded 7 times, then the average of these experiment would be 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 7 times, and 4 times plus 0 plus 0 plus 0 plus 0 divided by 11. This is just the average. 7 over 11 is also just the part of the of my winning flips of the coin. So then we now assume that we have asked 144 persons in Wilhelmshaven, and 75% of these would want to have the shops to be open on Sundays. So if they said yes, let's open every Sunday the shops, thumb up 75% of 144, and the other ones just said no. And in order to quantize this, then in your table you would insert a 1 for yes and a 0 for no. So calculate a confidence interval for the proportion of inhabitants of Wilhelmshaven that they would prefer general opening on Sundays with an error probability of 0.05 and alpha 0.1. Okay, well, at first we have to think that, again, this number of 30 translates now a little bit in another condition, which we have to check, that it is good to use the normal distribution as an approximation. So condition for normal distribution to be a good approximation. So if we insert this, then we have 144 times 75%. So we have 3 over 4 times 1 over 4. And this is then 3 times 144 is 532, I think, divided by 8. And this is obviously larger than 9. So check this condition. Then alpha equals 0.05 percent. Then 5%, 0.05. Then again, Z we have 1.96, and alpha equals 10%, in this case, we have z equals 1.64. So for the standard deviation, we can directly use, of course, our proportions. And then let's calculate sigma hat of pi hat equals square root of 3 over 4 times 1 over 4 divided by 144. And this is then square root of 3 over 16 divided by 404. And then we obtain square root of 3 divided by 4 divided by 12. And this one cancels. So we obtain 1/3 square root of 3. 3 is roughly 1.7 anything, and we obtain 0.577, only 2 sevens, sorry. So now we have collected all our numbers which we need, and therefore we end up with theta upper lower bar equals our probability 0.75 plus minus, first of all, alpha equals 5%, 1.96 times 0.577, and this would be then the intervals 68% and 82, roughly. And the other one, alpha equals 10%. Now we are shrinking together. The area under the density function, the probability mass is lower, not 95, but only 90. And so we obtain 0.75 plus minus 1.64. See, it is just scaling with this parameter coming from the normal distribution, 0.577, and then we have a smaller interval from 969 to 81%. So, and then we have a part B. Calculate the confidence interval if the confidence level, the confidence interval would be represented now with 0.75 plus minus 0.1. So now we are doing it the other way around. We have this interval 65%, 75%. And what we are now interested in is the scaling factor of the normal distribution. And for this, then we just take this formula and solve this formula for Z. Okay? So in this case, then, of course, we know that we have on the right plus minus 0.1. So this equals plus minus 10% is 0.1. So on the left, we have just 0.1, and therefore we obtain 0.1 equals 0.75 plus now unknown Z times, where do we have it? 0.577, and this means that we obtain, now where do I have my number? Tup, 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 tup. And z equals 2.77. And now we go with this value in our table. So I have a 2.77. We end up here. So we obtain an 0.9972. And this then equals an 0.56% error probability. Well, of course, since this is much broader than the interval corresponding to 5%, the error probability has to be much smaller, scaling by just a factor of 10. And next one, then we have a provider of mobile games, and he is collecting data, choosing 120 guys from our total users. And there we assume that we have really many users, not only 150, many users. So many users much larger than 110. We suppose that they are playing xi times, and the realization is normally distributed. And we obtain the following data, summing all numbers up. We obtain xi equals 21,840 and xi squared 4,886,856. So, having this data, again, we want to calculate a confidence interval of 99%. This means alpha equals 1%, and as we already know, 1% means a z value of 2.58. 99%. But of course, we need this one, and we need also this one, and this we have to calculate given these two aggregated data points. Well, mu is quite easy. Mu hat is x bar is then sum over x divided by n is 21,840 divided by 120, and this is roughly, where do I have my, there it is, roughly 182. Well, the other one, let's take at first the definition. Sigma hat squared of mu hat is equal to 1 over n minus 1 xi minus x bar squared. But we have only x sum over x and sum over x squared, so we cannot directly plug in our numbers, and therefore we can manipulate this formula. Just multiply the first binomial or second binomial formula, then we have xi squared plus, no, minus 2xi x bar plus x bar squared in brackets. Well, then we can further manipulate this 1 over n minus 1 sum, of course, since a sum of sums is just the single sums summed up. So we can rewrite this as sum over xi squared minus sum over 2xi x bar plus sum over x bar squared. Well, this, fortunately, we have. What about the other two? Again, 1 over n minus 1 sum over x1 xi squared. And now this is a constant, 182. This is a constant, and remember this summation operator is also a linear operator. So of ax plus b is equal 1 to n is a sum over xi, e equals 1 to n, plus now, and this is a constant, so I have to sum up a constant n times, means just n times the constant. So n times b. So, because you can just think of that you have here just a 1 in front of the b. So sum over a equals 1 until 123 over 1 is just 123. So this is then minus 2x bar sum over xi plus n times sum over, not sum, n times x bar squared. Well, and now we are almost done. This is nothing else than n times x bar. N times x bar, n times x bar minus 2 plus n times x bar squared. These two together is then just minus x bar n times x bar squared. But this x bar 182 we have also already, and then we can plug in all our numbers and obtain in the end, this is 100, let's say here 120, this is 182, and this was 121,840. Overall, we obtain a sigma hat of 86.767. So in the end, theta up down means 20 1840 over 182 plus minus 2.58 and square root, no, 86.67 divided by square root of n 120 is 182 plus minus 20.4. So calculate the confidence interval of the standard deviation. This is the same confidence interval for the variance given a confidence level. Did I missed anything here? Oh yeah. So this is B, of course. And here I haven't read it carefully. Calculate the confidence interval for the variance. So in this case, let's take this and put it in here. Part A, do not want to calculate a confidence level interval for x, but for sigma squared. And there we have learned, remember this, that the variance, the estimator, is chi-squared distributed. And for this, then, we have this formula, and y is, am I right, n minus 1 with, where have it? I have it in my head. S squared over sigma squared. S squared over sigma squared. So, first of all, we have to now get our S. This is the random variable corresponding to our variance sigma squared. So we can then insert our sigma squared we have calculated. And now coming back to this one, there we have then for theta lower bar, calculate n minus 1. This was 120 minus 1, and s squared, this we have out of our former, this would be then this number squared. Sigma hat squared is then 7,512. So times 7,512. Now, and we have to look in the chi-squared table, 1%. So 0.5%. Where do we have the 0.5%? Here. And our numbers, oh, I'm sorry, 20 is not enough, n minus 1. Hopefully I have the right table here. T-value, F Fisher, where's chi-squared? Oh, where's this chi-squared distribution? Where do I have it? Fisher. Here. Okay, done. Then we have to take estimation because I do not have the data here. Minus. Did I have obtained the whole data? And now I have it. Oops, this is enough. And again, zip, zip, and these numbers we need. And then let's go here and interchange this. Again, 50. And since we have only 100 and 150, then let's take this. And what we are now roughly doing, approx this by the mean of this. And this would be then roughly 125. And the other one would be on the right. And now we have to look up a second number since the chi-squared distribution is not symmetrical. So 0.995. And here we are at 128. And the average is then 20, 22, 11, 100, no, 12. 6 is then 134. So this divided by 125 and the other one, other way around, since we are dividing, of course, this is the upper limit and the lower limit. Yeah, here we have 1 minus and here alpha half, so 0.5 and 0.5% and 99.5% is 120 minus 1 times 7,000 over 134. Okay, well, this you can plug into your calculator and then you are done. And so we are done with our exercise for today. Yeah, then next week, hopefully over Easter, I'm able to give you the last part of this lecture because then hypothesis testing for the end. And next week on Thursday, we want to meet then together to do some exercises with hypothesis testing. Okay, thank you very much for today.